Today, we will see what kinds of hardwares are used in the MRI. The MRI consists of the static magnet, the gradient magnets, RF coils, and the computer. The computer is used to analyze the MRI signal using the Fourier technique to construct the MRI image. Thus, we will not further mention it here. We also see how the oblique images are obtained. We need the MRI image taken at various angles for the better diagnosis of the disease. Even though the gradient magnets are fixed in place, we can get the MRI images at any angle to any coordinate system. You will see how these oblique images can be formed today. A static magnet, we could get a larger amplitude MR signal with a stronger magnetic field. The strong magnetic field, on the other hand, may have certain harmful consequences on the human body. As a result, the FDA in USA advises against utilizing a magnetic field stronger than a particular upper limit, which is now around 30 Tesla. As an MRI magnet, homogeneity and stability of the generated field are required. A homogeneous field is required to avoid a short T2 star relaxation time and MR images that are distorted by field inhomogeneity. In order to eliminate undesirable artifacts, the field's high stability is required. Three different types of magnets might be utilized for MRI. They are permanent magnet, superconducting magnets, and resistive magnets. The closed bore system and solenoid structure are used in both resistive and superconducting magnets. Acquiring MRI imaging takes a long time. The patient needs to stay still inside the closed bore magnet during this duration. The quality of imaging can be affected by the patient movement. The patient also experiences claustrophobia when within the closed bore magnet. The open bore magnet structure might be used to reduce the claustrophobia of the patients. There are three different types of open bore magnets. The first type is permanent magnet in the shape of a C or U that produces magnetic field less than about 1 Tesla. The dipolar electromagnet, which contains coil and the patient is positioned between them, is the second type of open bore magnet. The coils could be superconducting or resistive coils. The magnetic field produced by this magnet ranges from 0.5 Tesla to 1.2 Tesla. The whole bar array or ring structure is used in the third type of open magnet, where permanent magnets are organized to provide a magnetic field only in the specific direction. However, this kind of open magnet produces a weak magnetic field, usually around 0.3 Tesla. This shows the C-shaped magnets and C-shaped magnet and Holbach array magnet and Orbit ring pair magnet. This one. Conversely, cross-wire magnets are solenoid type systems. The solenoid for resistive magnet is made of copper wires. If a current I passes through the solenoid, a homogeneous field mu0 Ni is produced inside the solenoid, where mu0 over 4 pi equal 10 to the minus 7 wave per ampere meter, and N is the number of copper wire turns per meter. So this number mu0 is very small number. So to get a higher magnetic field, we have to use very high current I, and also we turn as many turns as possible. We have to make as many turns as possible coils. The resistive magnet generates Joule heat as a result of the current passing through the resistive wire. The Joule heat is proportional to I squared times resistance of the coil is on wire, where R and I refer to the wire resistance and the current flowing through it, respectively. To create a strong magnetic field, we should increase the current magnitude. The amount of current we can apply to the magnet, however, is limited by Joule heat and the magnet's cooling. In addition, the fields in homogeneity and the stability are significantly temperature dependent. Resistive magnets are not extensively used for MRI magnets because of these drawbacks. Instead, superconducting magnets are commonly utilized for MRI magnets because they provide a high magnetic field with a low inhomogeneity and field stability. The superconducting wires are wound to form a solenoid for a superconducting magnet. With superconducting materials, electrical resistance in the superconducting state is zero. As a result, the superconducting wire can transport a large amount of current and generate a strong magnetic field. The most common superconducting wire is made of niobium titanium alloy. Below 9 Kelvin, this alloy becomes a superconductor with a critical magnetic field of up to 10 Tesla. The superconducting magnet is depicted schematically in the figure here. A liquid helium reservoir surrounds the superconducting coil. That's right, this is liquid helium. Liquid helium has a boiling point of 4.2 Kelvin, which is substantially lower than the critical temperature of niobium titanium alloy, which is 9 Kelvin. Because some liquid helium is lost due to evaporation, decayed helium must be refilled on the regular basis. No electrical resistance exists in superconducting wire. A current that has passed through the superconducting wire will continue to flow indefinitely. So, once the field is established, no electrical power is required to supply the superconducting magnet. So once current is established, we don't have to supply electrical power to the superconducting magnet. We can see some systems of open magnet MRI this way, and this one is MRI for animals, and use the permanent magnet. Next, see the gradient coil. Gradient coils provide a spatially dependent nuclear spin resonance condition in the human body. The simplest type is linear spatially varying magnetic field. The three gradient coils in the figure show the linear dependency of the field in the x, y, and z directions. So this coil gives a spatially dependent magnetic field along the x-axis, and here y direction, and here z direction. So using this gradient coil, we can get the spatially dependent field. They generate three gradient fields that are mutually orthogonal. The geometrical design of gradient coils is usually cylindrical, cylindrical shape, since they fit directly inside the bore of the cylindrical magnet for the static field. They are drawn to be placed separately in the figure. We draw separately here, but they are actually fitted together, so pressed together. The roles of these gradient coils can be switched from axial to coronal, sagittal, or intermediate slice orientations in most MRI systems. Next, let's see the RF coil. An RF coil is required to excite protons and also detect MR signals from photons. The RF coil is a magnetic energy storage device. The RF coil is basically a LC circuit. The resonance frequency of the coil is written as this formula. The coil's inductance and capacitance are represented by L and C respectively. So L represents inductance of coil, and C represents the capacitor connected to the inductance coil. So this inductance coil, and we put the capacitor here, and in this case we put several capacitors. Okay. There are two types of RF coils. volume coil and surface coils. The figure shows some surface volume coil examples. Okay. The saddle coils are used to image the wrist and knees. This saddle coil. The bird case coils, this one, on the other hand, are used for brain imaging. Okay. So these are volume coils. Static field is in this direction, and the V1 field is perpendicular to the static field. The left pulse's magnetic field direction V1 is perpendicular to the static field V0. The saddle coil and a singleton solenoid, this one, are used to image the extremities, the wrist and knees. On the other hand, the bird case coil is used in brain imaging. There are three different types of RF coils. One's for transmitting RF pulses only, so transmitting RF pulses only. The other one is for detecting MR signals exclusively. So this coil is used just to detect the MR signal. And the last one is for both, transmitting RF coil and detecting MR signals. So both functions are possible. Both sending and receiving MR signals are possible with the volume coils. Okay. On the other hand, the surface coil can only be used to receive MR signals. In contrast to volume coils, the imaging part is not enclosed by the surface coil, but rather is placed on the imaging region's surface. A wire loop, this one, wire loop, as in the figure, is the most fundamental surface coil design. This coil has a very high efficiency close to the coil. So it has very high efficiency close to the coil, but the field in the region away from the coil is extremely inhomogeneous. As a result, the surface coil is only used to detect MR signals and not to transmit RF pulses. This is coil for brain imaging, and this is for extremity, knee and wrist coil. We can see several RF coils for knee and brain imaging and wrist, and here the foot region, this knee region. Now let's see how we can get oblique slice imaging. For better diagnosis of illness, we require MR images of various slices taken from various angles. Figure depicts an example of brain imaging. The images of axial this slice is in the XY plane, this plane. So this axial image, coronal image, the GX, this GX plane, and the sagittal SYG plane directions are shown. We can also obtain images for the oblique slice. Besides these images, we can get the oblique slice, which means that we can obtain an image of this slice at any angle to any coordinated plane. Three graded coils are fixed in the plane, in place. So, how can you get the image of this slice at any angle you want? Three gradient fields should be perpendicular to each other. The phase encoding and frequency encoding gradients are on the slice plane. You can see for slice is in the XY plane, then phase encoding and the frequency encoding gradients should be on the slice plane. Okay. As also you can see here, slice is in the YZ plane, and so frequency encoding, phase encoding and frequency encoding gradients are on the YG plane. Also you can see the same thing here. While the slice selection gradient is perpendicular to it. Okay. If the image plane is XY plane, then slice selection gradient should be perpendicular to the image plane. Okay. The phase and the frequency encoding gradients are interchangeable in this situation, so we can exchange these two gradient fields. The functions of these gradient fields can be exchangeable. The directions of these three gradient fields for these slices in the YXY, YG, and ZX planes are depicted in the figure below. So you can see the image plane is XY plane, and here YG plane, and here image plane is in the GX plane. If the slice is XY plane, this one, the slice selection gradient is in the G direction. You can see here. And the phase encoding and the frequency encoding gradients are in XY plane. Yeah. Three gradient fields are perpendicular to one another, as indicated in the figure. Let's look at how we can get the gradient fields and the directions for oblique slices by combining the gradient fields and the directions for slices in the XY, YG, and the GX plane. When the coordinate system is rotated clockwise through the x-axis, the original and the new coordinate system have the following relationship. Okay. If we rotate clockwise through the x-axis, the old coordinate system and this new coordinate system is connected by this matrix. So we rotate through the x-axis, so here 1, and we rotate the angle by angle theta, then cosine theta, sine theta, minus sine theta, and cosine in this way. So matrix is given like this. The following are the relationship for rotating at the angle of theta through the y and z axis. So y axis, then here as well, cosine theta, sine theta, sine theta, cosine theta placed in this way. This is rotating clockwise through the y axis. And this one rotating clockwise through the z axis. This one here. And cosine sine are placed in this way. We already saw this, but let me mention again. Slide selection gradient. Image plane is in xy plane. Here. Slide selection gradient should be in the z direction. So GS is placed here. And if the image plane is in the YZ plane, then GS should be in the direction of X. So over here. And the image plane is in the XY plane. The slide selection gradient should be in the Y direction. Here GS is the amplitude of the gradient, which depends on the slide thickness. Okay, so for specific slide thickness, we can choose a specific gradient value of GS. Phase and frequency encoding gradients. For example, image plane is in the XY plane, then phase encoding gradient and frequency encoding gradient are in the XY plane. So in this way. So these are interchangeable. So we can put the phase encoding gradient here, and frequency encoding gradient here. We can interchangeable, just interchangeable, so we can put this G phi and GF can be used as GF. So G phi and GF are interchangeable. We can also obtain the directions of the phase and frequency encoding gradients for the image plane of XG and YG. Okay. So let's now let's see an example. Example 1. The image plane is made by rotating YG plane 45 degrees clockwise, which corresponds to the rotating 45 degrees clockwise through the z-axis. You want to choose image plane, this yellow plane, yellow one. So you want to make the image of this plane. Okay. So this plane is made by rotating YZ plane. This YZ plane, this gray plane, gray color, clockwise, 45 degree clockwise. That's 45 degrees. This one. This corresponds to rotating 45 degrees clockwise through the z-axis, right? So if we rotate through the z-axis by 45 degrees, you can obtain this yellow plane. So from gray plane to yellow plane, okay? So we rotate 45 degrees clockwise through the z-axis. So the matrix is given by this form. So rotating angle is 45 degrees here. So old system and the new system. So YZ plane, image plane is YZ plane, then this old plane, or this old X prime, Y prime, G prime corresponds to this gray plane, and X, Y, G correspond to yellow plane, U plane. So in old plane, in YZ plane, the slice selection gradient direction is X direction, right? So GS is put here. Then we can get this one. And phase encoding gradient in YZ plane, image plane, YZ. Then phase encoding and frequency encoding gradients are in the YZ plane. So one is in the Y direction, the other one is in the G direction. So we can get these numbers. Okay. So the results are given by these three matrices. So for slice selection gradient, both 0.707 GS along the x-axis, this x-axis, and 707 GS is a minus, right? So along the minus direction are used as the gradient for slice selection. Okay. So here GS is specified for a certain slice thickness. The phase and the frequency encoding gradients are interchangeable. So if we apply 0.07 GS along the x-axis and the same quantity 0.07 GS now along minus y-axis, then the slice selection gradient GS in this direction. Okay. And phase encoding gradient is the same thing. So 0.707 G phi in x direction, and 0.7007 g pi in y direction. That gives facing coordinate in the yellow plane. So also facing coordinate g pi, gf, and g direction. So this is interchangeable. So in the figure, this should be g phi, right? And this f, right? gf is in the g direction, so gf is in this direction. So using this kind of gradient fields, we can get the image plane is in the yellow plane. Let's see another example. In this example, we want image plane as gray plane, this gray one. So if you obtain a gray plane as our image plane, we have to rotate XY plane through the x-axis by the angle 60 degrees. Then we can get this gray plane. Okay. So the image plane, this gray plane, is made by rotating GX plane 60 degrees clockwise through the x-axis, right? Which corresponds to rotating 60 degrees clockwise through the x-axis. Okay. So we have this matrix 160 degrees here, and x prime, y prime, g prime correspond to the oldest system, that's yellow plane, and the new system is gray plane. Okay. So slice selection gradient can be obtained like this, and the facing coordinate g phi, and friction coordinate is obtained as this one. Okay. For slice selection gradient, 0.5 GS along the y-axis, and 0.87 GS minus, so along the minus z-axis are used as gradient for the slice selection. Here, GS is set for specific slice thickness. The phase and friction encoding gradients are interchangeable. So G phi phase encoding gradient is x direction in the new coordinate system. So it's correct, right? This is the x direction. This x direction. And friction encoding gradient, if you use 0.87 GF y direction and 0.5 GF the g direction, then you can get this frequency encoding gradient. Okay. If you use 0.5 GS to the y-axis and 0.87 GS along the minus g direction, then you can get this as size selection gradient. Now, final example. Let's obtain YG image plane. So final one is this one, blue plane, starting from XY plane. This XY plane, yellow plane. We already have the slice selection gradient is in this direction. If the image plane is in the YZ plane, you already know, okay? And G phi and GF should be in this direction. But if we start from XY plane, then first we rotate XY plane through the x-axis 90 degree. Okay, then we can get the XY plane, right? And then we rotate this XY plane through the y-axis, the angle 90 degree, we can get finally the YZ plane. Okay, we just want to check from XY plane to YZ plane. So XY plane first can be obtained by rotate, no, not this one. It's YZ plane. It's not XY plane. It's YZ plane. So YZ plane, this blue plane, can be obtained by rotating XY plane, this plane, 90 degree clockwise through the x-axis. Then we can have XY plane, and then rotating this XY plane 90 degree clockwise through the y-axis, then we can get finally have the YZ plane as our image plane. Okay, so the matrix through the x-axis, okay, and next through the y-axis. So this old system, this means yellow plane, and XYZ, this new plane, this blue plane. Right? Then we can get this matrix. So this matrix represents rotation 90 degree clockwise through the x-axis, and this gives the rotation 90 degrees through the y-axis, right? Then we can get the YZ plane from XY plane. Slice selection gradient. This is old image plane, XY plane. In the old XY plane, the slice selection gradient direction is y direction, y axis y. So this y axis y. And new coordinate system, blue plane, we have the slice selection gradient in the x direction. So we already know this, but we just check. Okay. So x-axis slice selection gradient is in the to the x-axis, which is as expected. Okay. Phase encoding gradient in old system, old coordinate system, phase encoding gradient is in the xg plane. So in old coordinate system, let's choose x-axis as a phase encoding gradient. Then we can get new or phase encoding gradient in the new system, new coordinate system. That's the g direction. Okay. Frequency encoding gradient in old coordinate system, g direction, and new coordinate system, y direction. So that's the direction. So we can check the three gradient fields, if the YG plane is the image plane. So we start from XG plane as the image plane by rotating this old image plane 90 degrees through x-axis, and next 90 degrees through y-axis. Then we can get new planes. This blue plane is as new image plane. So in this way, we can acquire slice image at any angle to any coordinate plane. So which some examples demonstrate this one. So we can get the oblique image using this kind of manipulation.